Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of car features. So we have a bunch of different cars, we have the make, model, year, and then a bunch of other features such as the engine type, horsepower, transmission type, whole bunch of things. At the end, all the way over here, we have the MSRP, which is the manufacturer suggested retail price. So we're going to try to predict the retail price of a given car, or the suggested retail price, based on all the other features. So let's hop into the notebook. I'm going to be using NumPy and Pandas just for working with the data. Then for pre-processing, we'll use the train test split function and standard scalar from sklearn. And we are going to do some dimensionality reduction with principal component analysis today, because we are working with a large number of columns once we do the full encoding of the dataset. And because we're training on a whole bunch of different models, just for the sake of this video, I want to speed up the training time. So we're going to reduce the number of columns using PCA, just so that we can train all these models without waiting 20 minutes or more. So let's import all of these, and we can load in the data using pandas.readcsv. And I'll grab the file path to the data up here, paste that in, and we can take a look. Alright, so we have 16 columns in total. This is what we're trying to predict at the end here. And I just want to get a little more information on the data using data.info. So we do have some missing values in a few columns. In addition, we have 8 object columns, which we are going to have to encode. So let's start pre-processing. And I'll create a function called preprocess inputs. And this is going to take in a data frame, and it's going to make a copy of the data frame. And then it's going to return the data frame. So right now it just makes a copy. I'm going to store the processed version of data in X. So we'll pass data into the function, get it back in X. Right now this is just the same exact copy, but now we can change it in the function. Alright, so the first thing I guess we should do is try to figure out what is the nature of our categorical variables. We know we have missing values, but before we can go about filling them, we want to know how we're going to encode each column. Because based on how you encode categoricals, you'll fill missing values differently. So we can get a good sense of the categoricals based on, for example, how many how many unique values are in each column. So I'm going to create a dictionary here that's going to map the column name. Let me just zoom up on this a little. We're going to map the name of the column to the number of unique values in the column, and we can do that by taking the length of x sub column dot unique. So we take the unique values of the column and then take the length to get the number in the column. And that's going to be for every column in, now I could do x.columns to get every single column, but I don't really care about the numeric values. I don't really care to know how many unique values we have in the horsepower column. So I only care about the object columns. And we can target only those object columns with the select dtypes function, where we pass in the data type we'd like. So we are just looking at the columns of that have data type object. Alright, here we can see, so we have make and model, engine fuel type, transmission type, driven wheels, market category, vehicle size, and vehicle style. So the only one here with sort of that's sort of alarming, not alarming, is this model column has 915 values, and they're all independent of each other. There's no ordering between them. So this is a nominal feature with a high, you could call it a high cardinality feature, because the number of unique values in it is very high. Now, if you have a lot of time and computational power, this really isn't a problem. 915 unique values is really not an issue. But because we are working on sort of a limited scale here, this could be it's sort of pushing it. Because we'll be using one-hot encoding, since it's a nominal feature, we'll generate some dummies columns for that column. So we take the model column and use pandas.getDummies, and you can see it'll take each unique model, send it to its own column, and we'll get a one-hot vector for each example, where the 1 corresponds to the original value of that record. So you can see here this is 915 columns, and so the higher cardinality a column has, when we one-hot encode it, the more columns we have, therefore the more features we have, and therefore the slower our model's training will be. So what I'm going to do, because I don't want to lose out on this information, we could drop it if we were really feeling lazy, but what I will do is I will encode it. I'll put all these 915 columns onto the data, but then I'll use principal component analysis to reduce the dimensionality of the data back down, while hopefully saving a sufficient amount of information from the dataset. So let's do that. We're going to one-hot encode this, and we also want to figure out which of the others we're going to one-hot encode. So what I'm looking through here for is ordinal features, features that would not be one-hot encoded, but instead be ordinal encoded. Now we have to be careful with ordinal features. For example, I think there is one in here. Where is it? Vehicle size. Okay, if we look at this. If we look at vehicle size and take the unique values in that column, there's three different values: compact, mid-size, and large. Now, one way to encode this might be maybe to set compact to 0, mid-size to 1, and large to 2, because the model would then be able to see it as a range of values. It would be able to understand that large is greater than compact, that mid-size is lower than large. But there's sort of an inherent problem in here, is that we don't know how much larger large is than mid-size, or how much larger mid-size is than compact. The spacing between those values, using 0, 1, 2, is sort of arbitrary, and we're choosing it, and we don't really know the spacing between these values. So if it's sort of ambiguous like this, I don't know. It really comes down to what works best, but we could just do this as a one-hot encoding to sort of skip out on the ambiguous nature of the variable. There are like other variables such as like month. You can encode very easily because you know that each month is separated by the same amount of time, so you can evenly space it across a scale. But for something like this, I think it is a bit ambiguous, so I'm going to one-hot encode this as well. So let's go through each object column. I'll actually just get all the object data types down here with x.select data types, select d types, select d types object, and that will just give me the actual columns, so I can look through and sort of try to figure out which of these we're going to one-hot encode. So the make will definitely one-hot encode because there is no ordering between these values. The model we also will one-hot encode, like we said. The engine fuel type, this is also not ordered, so this is a nominal feature. We will one-hot encode this. The transmission type, there are only 5 values in here, but we can sort of figure out that these do not have an order either. Driven wheels, so yeah. You can't really order these values either. There's no good way to do it. The market category. So this is an interesting column. This is a column. It's a categorical column, but we have multiple categories for each value. So this basically this uses a kind of encoding that some people refer to as multi-hot encoding. Essentially, what we'll do is create dummies like we would for one-hot, but we'll include multiple ones in that one-hot vector. It will be a multi-hot vector because, for example, we could take all the unique values in this column, separated by commas, and then, for example, for this example, we'd have ones in the crossover column, the hatchback column, and the luxury column, and zeros in all the others, such as factory tuner. So we're going to use a multi-hot encoding for this. And then for vehicle size, like I said, we are going to do a one-hot encoding. I'm not sure the ordering between these values. And then vehicle style, also no ordering between these, so one-hot encode. So essentially everything is being one-hot encoded except for the market category column, which we're going to multi-hot encode. Alright, so I would like to do the multi-hot encoding first. So I'm going to create a function up here above our pre-processing function. I'm going to call it multi-hot encode. Now I would like to point out, before we perform a multi-hot encoding, we are going to need to fill the missing values. The reason being, we're going to have to perform some sort of splitting on the strings, on the commas. And we can't call a split function on a missing value. So we can just fill the missing values with an empty string, or I guess what I'll do is fill it with the string missing. So we'll take the market category column and call fill NA to fill any missing values with whatever we give it. And I'm going to fill it with the string missing. And that's going to be the new column, like that. So fill multi-hot column missing values to begin. Alright, so here's our function. So I'm going to start off by creating a copy of the data frame, just so that we're not modifying the original. And what I want to do to start is I want to count up all the unique categories across all of these examples. So I have to go into each one, split by commas, and then get each value in between columns. So we'll have factory tuner, luxury, high performance, performance, and then it keeps going until it finds new ones. Crossover, hatchback. Yeah, and we can't see any others on here, but I want to collect them all into a list. So we can do this sort of like this. We can create this all categories. And to get all categories, I guess I'll demonstrate here. If we take X, which is just our data right now, and we apply a function to it. Actually, I want to apply it to just the market category column. So we take market category, and we're going to apply a function. It's a lambda function that maps any X, which would be one of these, to the split of that X, so on a comma. So I'm going to take one of these, I'm going to split it on comma, and then I'm going to take a look what that looks like. And you can see it took each string and split it into a list. So now we have all the categories in their own places within lists instead of in the strings. So what I can do now, if you remember, we can concatenate lists like this. By adding two lists together, we actually just splice them together like that. So if I call the dot sum on this, and I'm summing down across the series, we'll actually just concatenate all of them together into one big list. What's nice now is I can now use NumPy's unique function to grab all the unique values in that list. So here they are. These are all the categories in the whole column. So let's grab this and put it up here for all categories. And we're going to do that for any DF and any column. And then once I have these categories, I'm going to go through each category, and I'm going to extract. I'm going to construct the ones and zeros for our multi-hot vectors. So for each category, in all categories. Alright, so this is a bit interesting. So for this, what we're going to do is we're going to apply a function to the whole data frame. And so this is interesting. Look, if we take X, now if we take for example the make column and we call dot apply on it, whatever function we pass into the apply function will be called on every single one of these, right? Going down the list. So if we call apply on a series, we will get it will apply it element-wise down the series. However, if we call it on the whole data frame, this will apply it to every element in the data frame. But if we include axis equals 1 in here, this will apply the function to every row by row in the data frame. And so whenever you're trying to apply a function to using multiple columns at once, this is a good way to do it. You use the apply function, but specify axis 1 so that you're modifying a whole row at a time, going down like that. And this is a lot faster than actually iterating through the rows. The last thing you want to do is iterate through the rows. It can take so long. So, all right, let's do this. So, I'm going to basically, in here, take our data frame and call .apply on it on axis 1, like I'm doing down below. And the function we want to apply is a lambda function that takes an x. In this case, because we have axis 1, an x is going to be the whole row. And it's a pandas series that still has the column names built in. So we can harness elements of that row by indexing at the column names. So we're going to set x to 1 if the current category that we're on is present in x subcolumn. So if you remember, column is the market category column, and for a given row, we're going to create this new number 1, but it'll only be 1 if the category, which for example factory tuner, we're just iterating through this whole list to get the categories. If a given category is present in the market category column, so if category in x subcolumn, then we'll set x to 1. And otherwise, we'll set x to 0. And this will actually create the binary columns, the binary feature column for each category in all categories. So what I'll do is I'll create a new column to store it in now, which I could call it df subcategory. So we'd have a column called crossover, a column called diesel. But I just wanted to avoid ambiguity. I'm going to include the column name in the column, include the market category in the column name. So it'll be market category underscore and then a category name. Alright, so I know this is, I'm just sort of talking about it, but let's actually see what this looks like. I'm going to return the df, and we can now call this function multi-hot encode on our x, and the column is going to be market category. And here it is. So if we go to the end here, you can see our multi-hot columns. This is the reason it's called multi-hot is because it's sort of like a one-hot column, but there's multiple ones in it, like I said before. And you will notice we have a missing. There should be, right here. There's a missing column. If the original value is missing, we'll have a 1 here. Now, whether you want to have this on is sort of up to you. It's not necessarily essential, because one way of encoding a missing value is just by having all zeros across here. So yeah, you can definitely drop that column if you like. I'll just keep it, but yeah. So last thing I want to do is actually drop the original market category. Now just to confirm that this is working properly, I'm going to look at this. Market category for the first row here has factory tuner, luxury, and high performance. So if we go over here, you'll see we have a 1 for factory tuner, a 1 for high performance, and a 1 for luxury. We have zeros in all the others. I noticed we have a 1 in performance, which is interesting. Let me take a closer look at that. If we use loc to grab the first row and the market category column, we have factory tuner, luxury, and high performance. So those are all working well, but we also have ones for just performance, which let me just take a closer look at this and figure this out. Okay, I figured out what the issue is. It's because we're checking if the category is in X sub column. And if you remember, we haven't actually performed the split on the column. We're checking if it's in the string, essentially. So if our category is performance, right, so if it's right, so let's say our category is performance. We're iterating through, we're looking at each one, we get to performance. We check if performance is in X sub column, which refers to this thing. And we notice that performance is in X sub column because this is a string. So we have to make sure we split this first, so that we're not checking if it's in the string, but we're checking if it's in the list. So up here, before I get all the columns, I'm actually going to take the column and apply a lambda function that maps x to x.split on commas. And then over here I don't have to do this. Instead of this, I'm just sum across it. So first we'll actually set the column to be lists instead of strings. Then we'll sum across the lists to concatenate them and get the unique values. Now down here, when we check if it's in X sub column, we'll be checking if it's in a list rather than in a string. So let's check that now. We should see zeros here instead of ones. And there we go. So now we only have a 1 for factory tuner, a 1 for high performance, and a 1 for luxury. And that corresponds to factory tuner, high performance, and luxury. So it looks like it's doing well. So now we don't need this column anymore, so the last thing I'm going to do is drop it in here. So we're dropping column from axis 1. Okay, here's our multi-hot code and function and encode function, and it has been completed. So here are all of the encoded values. Let's just plug it into our pre-process function now. We'll say multi-hot encode the market category column. I'll just say one hot encoding. Alright, so remember this function that we created returns a data frame. Let me just clean this up a little. So we're going to store the result of this back in df. And we'll call multi-hot encode, passing in df, and the column we'd like to encode is the market category column. Alright, now we'll do our one hot encoding. And for one hot, we were going to one hot all the other categorical features. So we can do this sort of simply. We just say for each column in x.select dtypes object dot columns. So for each of the object columns, we will call one hot encode, passing in df, and our column is column. So once we've done the multi-hot encoding, we're just going to go ahead and one hot encode all the other categorical columns or object columns, because we already verified that we need to do that. So I didn't worry about the missing values for these one hot columns, because one hot encoding will already take care of the missing values. The only reason we had to do it for this is when we try to split it, it won't work if there's missing values there. But when you one hot encode, basically the one hot vectors will just be all zeros if there's a missing value there. Alright, so let's take a look. And this is when we get the high dimensionality. Oh, not defined. Oh, we didn't create the function, sorry. Let's create our one hot encode function, which also takes a data frame and a column, creates a copy of the data frame, and then we just, hold on, it's indented badly. So this is much easier. We're just going to use the pandas function getDummies that I showed earlier. That will take in the column and get the dummies for it, store it back in dummies, and then I also want to include a prefix, which is similar to what we did here by adding the column name at the beginning. So we'll keep the column name on, that will come on with an underscore for each dummy column. This way we can know where the dummy columns are originally coming from. And then once we have our dummies, we want to actually add them to our data frame. So I'm using pandas.concat for concatenate, and we're going to concatenate the df and the new dummies side by side, so axis 1. And we'll store the result in df. Last thing to do is just drop our column, the one we created the dummies from, since we no longer need it. Alright, that is the one-hot encode function, and we can now just run this on each of our object columns. And now we're going to get the high dimensionality data. Oh, we're getting another one. Market category. Oh, I put X in here. It should be DF. Okay. So now, like I said, now we're getting the high dimensionality data. We have 1,000 columns. So there's quite a few columns. It's a very sparse matrix now. So we're going to use dimensionality reduction to reduce the number of columns we have. So the last thing to do is fill missing values for the numeric columns. Let's see how many more missing values we have. We can call isNA to get the, it'll be a true or false in a given location. A true will denote a missing value there. So we can sum this down the rows to get the total number in each column, total number of trues, or total number of missing values. And we can sum again across the columns to get the total number in the whole data frame. So there's 105 remaining missing values, and we can actually check where they are by just summing over the rows to get the total number in each column, and then asking, is a given column's missing values greater than 0? And we'll have a true wherever there is, and I can use this true false as an indexer for x. Actually x.columns. And so these are the ones that had true. So there are only 3 columns that have missing values, and that is the engine horsepower, engine HP here, the engine cylinders, and the number of doors. So these are the only 3 right here with missing values. And we just want to fill that before we go any further. So when we have numeric values, we can just fill with some statistic about the column. Now it's important to sort of choose your statistic wisely. For example, with horsepower, this is a continuous range. It's a float, basically. So we can use the mean. Makes sense. However, for cylinders, and especially for doors, using the mean would be sort of weird, because you can't have 1.5 doors. You can't have 1.5 cylinders. So we're going to use the mode. That way we just get the most common occurrence, and that will solve that problem. So we'll fill remaining missing values. And for the engine horsepower column, we're going to use the mean. So we're calling fill NA on it, and we're going to fill it with engine HP dot mean, like that. And let's store that back in the column. And then for each of the other ones, so for column in, I think it was engine cylinders and number of doors. So like this. For each of these ones, we're going to fill the column, fill NA, with df subcolumn dot mode instead. Now, I do want to point out when we're using mode, for example, let's take this. We'll take engine cylinders. This is supposed to be X. And we call that mode on it. Like this, actually. It actually returns a pandas series. I'm not sure why. Mean does return a numerical value. Mode returns a pandas series. So if we want to get the actual number value, we should subscript it for 0, and that way we'll get the actual number. So in here, I'm just going to subscript 0. Okay, and then let's store that in df subcolumn, like that. Okay, let's see this now. We run this, process our data, and then we check the total number of missing values in our data. Where is that? Here. I'll do this. I'll sum over both axes to get the total number of the whole data set, we have 0. So we're totally done with missing values. We're totally done with encoding. Our data is fully numeric. All we have to do now is split and scale the data. So first let's split. So y is going to be what we're trying to predict. That's just our vector of retail prices, which was given by the MSRP column. So y equals df sub MSRP. And then x is all the rest of the data. That's going to be our feature data, what we're using to try to predict MSRP. So we're dropping MSRP from axis 1. And so this has done the vertical split, or I guess horizontal split. I don't know, however you want to think about it. It's splitting the column off from the rest of the data. And then we'll do our train test split. So this will take 70% of the rows, throw them in the train set, and then the other 30% will go to the test set. And for this, we can use the train test split function from sklearn. Great function. You just pass in the values you want to split, specify the train size. We can do 70%. This also shuffles the data for us, so we don't have to do that. And because it shuffles, I'm going to include a random state to seed the function so that we always get the same shuffle and therefore the same split whenever we run this notebook. So we can reproduce the results. And that will return 4 new sets of the data: xtrain, xtest, ytrain, and ytest. Alright, and let's return those sets of the data instead of df. So that's going to be what the function returns. And we can get xtrain down here to see. It should just be 70% of the original data. We originally had 11,000 rows. Now we have 70%, which is 8,300. And we don't have the MSRP column. So that has been put into ytrain. So these are our targets, and these are our features. Okay. So the last thing that I want to do is scale the data. So right now, all of our features take on different varying ranges of values. We have a range of 0 to 1 over here, and up here goes into the thousands. Up here it stays in the like near 2000. So we want to standardize the columns with a standard scaler. The standard scaler is from sklearn. Basically, that will just give each column a mean of 0 and a variance of 1. So we'll just do a shift and a scale on each column. And this improves the performance of many models. Many models will benefit from having scaled data inputted. And we'll fit the scaler just to the train set, because we sort of want to pretend we don't have access to the test set when we're doing this pre-processing. But it wouldn't impact the performance too greatly if we did fit it to the test set as well. It's just, I feel, good practice, because in practice you wouldn't have access to new unseen data when you're doing the scaling, the fitting of the scaler. So then we will call scalar.transform to actually transform both the xtrain and the xtest. We'll do the xtest next, and I want to store that back in xtrain. So the only problem with this is that scalar.transform will return a numpy array. So for example, if we do this, and I just change these to xtest, when we get back xtrain, all the data is there, it's been properly scaled, but we just can't see it like a nice data frame anymore. So what I like to do is turn these back into data frames right after they've been scaled, and make sure to keep the indices the same as they were before. So index equals xtrain.index, and the column names the same as they were before. So columns equals xtrain.columns. And down here just has to be xtest. Alright, and that should do it. So now each column should have means very close to 0 and variances very close to 1. And we can confirm this with xtrain.mean. Yeah, they're all very close to 0, and xtrain.variance, all very close to 1. Okay, so we're done. Pre-processing complete. Now we can start training. So I'm going to do training on it with a whole bunch of models today. Here they are. We're going to use a simple linear regression model. Then we're going to do linear regression with L2 regularization, which is ridge regression, and linear regression with L1 regularization, which is lasso regression. Then we'll use a k-nearest neighbors algorithm, a neural network, 2 support vector machines, one with a linear kernel, one with a nonlinear kernel, then a decision tree, and 2 ensemble methods, a random forest regressor and a gradient boosting regressor. They're both tree-based models. This one generates trees in parallel, this one generates trees in series. So, just for the sake of time, I'll copy this in. It's a dictionary that maps the name of the model to the actual model instance. And this allows us to iterate through for name and model in models.items. So for each pair, key value pair, items will get them as tuples so that we can iterate 2 at a time like this. We're going to fit the model on the train set, and we're going to print out a little confirmation message that says the model was trained. And so here we go. Now, this is going to take a while. I don't even know how long it's going to take. The first few models will train quickly. As soon as it gets to the neural network and the support vector machines, it's going to slow down really hard. So what I'm going to do is dimensionality reduction. Now this isn't essential. If we were willing to commit the time, we absolutely could train, and we get a higher higher R² score most likely, lower loss. But this is also a good way to just sort of use principal component analysis. And let me just paste this in. It's a little markdown block. We have a very high number of columns for our purposes. So let's reduce the data using PCA to have only 100 columns to increase training speed. And so we're going to use the PCA object from sklearn, which I imported earlier. This takes in a number of components that we'd like to reduce to. And n components we will specify up here. I'll make it 100, so we'll just reduce it down to 100 columns. And so principal component analysis is basically a way of shifting the way you're looking at the data, redefining the features. So by itself, the algorithm isn't it doesn't perform the dimensionality reduction. It just changes the definition of the features by shifting the way you look at the input space. So normally, especially after scaling, it's actually important that we center at 0, and if we're doing this, all the variances are more or less the same across all the features. Now when we use PCA, it sort of finds that shape of the data in the input space and shifts the definition of the features so that the first feature is the axis along which the data varies the most. The second principal component, or the second feature, is the perpendicular feature, feature that's perpendicular to the first one, which is the second, the axis along which the data varies the second most. And it goes in order. So you have the most variance in the first principal component, the second most variance in the second principal component. And you can sort of, this is sort of a way of capturing most of the information in the model in the first few features. And so the dimensionality reduction happens after this calculation has been done, where you just chop off the last principal components. In this case, we have 1,000 features, 1,019 features. So we would get 1,019 principal components, but since all the variance is contained in the first, maybe let's say 100, we can just remove the last 900, and then therefore reduce the dimension of the data. So we create our object, and I'm going to fit it pca.fit on the train set. Now I'm only doing it on x because we don't care about y in this case, and we're going to. Oh, it actually did. Yeah, I'm not sure if this next one will train. It's taking a really long time. But right, so we're doing the same thing we did earlier, fitting only to the train set and transforming both the train and test set, like so. Now I do want to make this a data frame as well, like I did with the scalar, because this does return a NumPy array. So we keep the indexes the same, xtrain.index, but the column names are going to be different. I'm going to give column names of PC1, PC2, PC3, all the way to n components. So we can do that like this: PC plus string of I for I in range 1 until n components plus 1. And that will just give us PC1, PC2, PC3 up to PC100. And we'll do the same thing for xtest. Oh, whoops. So we'll just change these to xtest and perform the PCA. Now this might just take a moment. It won't take too long. Definitely not as long as this will take. And once that's done, you know what? I'm going to cancel this. I want to do xtrain reduced here, and xtest reduced. So I did just cancel the training by pressing stop, but I don't want to overwrite xtrain and xtest. So we'll run that, and then I'll take a look at xtrain reduced when it's done, and I will resume the video as soon as it finishes. Alright, it finished, and we have 100 columns now. The variances of these, if we take a look, are decreasing. We have the most variance in the first column, then second most variance, third most variance, all the way down until we're back to a variance of 1. So we can sort of hope that all the information required to get a decent performing model was contained in these first 100 principal components. Now there's no doubt we're losing information. We are losing 900 features worth of information, but they're the least important features in the data, at least in terms of the principal components. So let's try training now. And I just want to train on xtrain reduced instead. So this model will take 100 features each, and you can see it's already going much faster. This still will take some amount of time, but it will not be nearly as long as before. So once we're done, we'll print out the results. I'm going to iterate through the model dictionary again with name model in models.items. And we're going to print out the name of the model followed by the r² score. And r² score is a good way of getting a sense of how your model's doing if it's a regression model. It's basically a measure of how dispersed the data is around your fit. And we're going to format this with model.score, which will return the r² score for a regression model. And we'll pass an xtest reduced and ytest, and evaluate it on the test set here. Alright, so the models have finished training, and I'll go ahead and check the r² scores. So, alright, there they are. It looks like our linear regression models did fairly well. These guys didn't do so well. Neural network didn't do so well. And both of our support vector machines really sort of bombed. R² score, the highest value you can get is 1.0. The lowest value, there's no limit. It can go deep into the negatives. So this is still not great. It's less than 0. But the rest of our models are doing fairly well, except for the neural network. So k-nearest neighbors did all right, and then the linear regressions are a little higher than that. But our tree-based models really took the cake here. They did very well. 0.84 r². Random forest actually came in first with a 0.846. Now, we may be able to get better fits if we didn't do the dimensionality reduction. If we saved all that information and we just trained on the original data, we may get higher r² scores across the board. But this is still decent performance for what we did. So that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.